here we have our stress strain analysis project. So the three things that I was looking for was our yield point, yield strength, and elastic modulus. The yield point is the point at which the plastic deformation starts. So on the graph, that's where it'll go from being linear to more of a parabolic shape. And that's where the specimen will stop acting elastically and start acting plastic. The yield strength is the exact stress value at that point on the graph. And then the elastic modulus is the material's resistance to elastic deformation. And that is going to be stress over strain. So using that, we have our curve drawings, which we're measuring stress over strain. For the yield point of steel, we found it to be roughly 150 megapascals. And that's where the plastic deformation would start. For aluminum, we found that it was roughly 200 megapascals. And copper, it was roughly 60 megapascals. So using all that information, in order to find the elastic modulus, we were looking for the slope of the linear part of the graph. So to do that, I found the change in the stress over the change in the strain. So for aluminum, I converted all of the values. I changed the megapascals to gigapascals, and then the percentage strain I changed just into a regular decimal value. So using the point of the yield point and then the original point, we got that its elastic modulus was roughly 59 gigapascals. And then the same thing for the steel with the same conversion. We found that the elastic modulus was roughly 145 gigapascals.
Figure out the percent elongation and percent reduction area for the aluminum. We took the change in length over the initial length for each piece, and we're multiplying that by 100 to get a percent. So the percent elongation, or the change in length for this aluminum specimen, turned out to be 6.1819 millimeters, and the original length of the entire specimen was 7.4 inches. So we converted the millimeters to inches, and then did the division and multiplied it by 100 to get a percent elongation of 3.2842%. And then we did the same for the reduction area. We took the change in the area over the initial cross-sectional area. Again, multiplied it by 100. This one was already in inches, so there was no conversion needed. And once we did the math for that, it came to negative 19.834%. So the area actually shrunk, and the length of the specimen actually increased. Now, we did the exact same thing for steel, same thing for the percent elongation. It was measured in millimeters, had to convert it over, and we divided it by the initial length of the specimen, which was 7.4 inches again. Once you did that, did the math, we got 11.9419%. And then for the percent reduction area, took the change in the area over the original cross-sectional area. We calculated the change, divided it by the original cross-sectional area of the piece, multiplied it by 100, and got negative 61.728%. So the steel was able to stretch a lot more and shrink more than the aluminum. So it's more plastic-like in a way. Then for the resilience of each piece, we took the yield stress, squared the yield stress, and then divided by 2 times the elastic modulus. So the yield stress at the yielding point was 205 point something megapascals. So we multiplied that by 10 to the 6th to knock out the mega. And same with the elastic modulus, which is measured in gigapascals. Multiply that by 10 to the 9th to knock off the giga. Once we worked all that through, it came down to a very big number in regular pascals, but it was about 0.3515 megapascals. Same thing for the steel. The yield stress, squared it, divided it by 2 times the elastic modulus, worked all that through, and came out to about 0.09345 megapascals. Now to find the toughness of each piece, we took the area underneath each of the curves. Now there wasn't an actual equation that we could integrate to find this more accurately. So we just took it in blocks. So this first block is 250 by 0.12, and then we add on this next block of 50 times 0.08, and then that last block there of 150 by 0.02. This gave us 37 megapascals for the toughness of the aluminum. And for the steel, did the exact same thing, broke it up into blocks. So 200 times 0.4 plus 50 times 0.35, that's the top, and then plus 100 times 0.05, giving that little block at the end, and that came out to 102.5 megapascals.
Alright, so next for your task was finding the tensile strength of each of our materials that we found. So if you see over here, we have the graphs of each of our materials. So we found this one online for copper, this one's for the steel, and then this one is for the aluminum. So in order to find the tensile strength, you have to look and locate where the peak of the graph is. So right around here is the peak for each of them. So you're looking at just the highest point. And then once you find this highest point, that's going to be the ultimate tensile stress that it can withstand. So for copper, it doesn't really have a set value because we didn't have the data that it was plotting with. But if you look at the graph, the peak happens around like 220. So I just assumed it's around 220 megapascals. And then for steel and aluminum, we have the data for it. So if you go through the Excel sheet and you look for where the force is the highest, it'll correlate to how much megapascals that's going for. So we found that for aluminum, it was 271 megapascals, and then for steel, it was 315 megapascals. And then next, there was an interesting question about Spider-Man analysis. So we had to find the silk and see how much stress the silk had to be able to withstand in order to hold the Long Island ferry. So it's not a lot of things are given in this equation. So you have to use some, assume some things. So for the web, I just assumed it was around 2 inches in diameter. If you analyze this picture from the film, you can get kind of a lot of the information that we were working with. So the diameter of the web looks to be around 2 inches. And then for the weight of the ferry, in order to find how much force it needs to be able to withstand, I found the weight of the ferry online. There wasn't really an exact detail, but I assumed that the weight of most ferries is around 4,000 tons. And in the film, it's shown that it has a couple hundred, probably 10, 15 cars on it. So just adding the weight of all the cars and then on the ferry, I found that it was around 5,000 tons. So our task is to find how much stress this web would need to withstand from this point and this. So how much force is pulling on that web for it to be able to withstand. So if you look at the movie, it's around, there's some geometry there going on that you can assume. So this weight of the ferry, you find the components in the x direction for it. And the formula for stress is the force over the cross-sectional area. So the area of a silk, I found that if it has a diameter of 2 inches, the area is just pi, due to pi r squared. And then, so if you find the diameter for the area, and then the force, converting the tons to kilograms, and then multiplying that by the gravitational constant, I found that it took over 4.9 times 10 to the 7 newtons. So there's a lot of force that's being pulled on the web, and then such a small area. So I found that the stress needed to withstand is around 3.85 times 10 to the 7 Newton meters squared. And then using that, we also have to find the elongation that this web would need to be able to stretch and hold that ferry together. So in the film, it shows that if you assume his Wingspan is around 6 feet. You just like assume where it could be. So we assume that it starts off at around 12 feet. And then if you play the movie, you'll see that the boat starts tipping more and the silk begins to stretch. And then I assume that it stretched to around 15. And so the elongation formula is just the change in elongation over the original. So I found that it was around 25% elongation. And so finding all this tells us that in order for the silk to be able to hold that ferry together, you would need 3.85 times 10 to the 7 Newton meters of stress, and it needs to elongate to at least 25%.